So hello and welcome back to another video, again on my graphics tablet, and today I'm going to do what I call GPU basics. So this is it's not on the level of understanding you require to watch the other videos. So this is a pretty simple one. It is for the people who have a graphics card and they take the cooler off to change the thermal paste, and they look at their PCB and they ask themselves, what is what on this, and how do I find out what exactly I've got, and maybe find out how good it is. Or maybe you are more interested in PCBs and above average level overclocking, I would say, and you're just starting out and you don't really know how to find out what you've got on a PCB. And so I'm going to explain how I do my stuff, and I'm going to talk about some common things you will see when you have certain graphics cards. So right here I've already made a sketch of how a graphics card PCB basically looks. That's pretty much all the important areas. And then down here I've got 6 pictures. The 3 left ones I've got from the internet, and then the 3 ones on the right I took myself. So the first, we have a GTX 1060, a model from Gigabyte. Then we have a GTX 980 reference PCB, a RTX 2080 reference PCB, and then here we have my GTX 560 Ti 448, which is MSI, then my GTX 470 reference, and my ASUS GTX 980 Ti. So, and all of these cards are slightly different, but I think you can already make out certain things that they all have in common. Like this. Yes, this is that basic. So all of these have this one big chip in the middle. It's a little smaller on the GTX 1060, but it's still the same thing. That is the GPU, the graphics processing unit. That is what makes all the magic happen. That's the main focus of every graphics card. That's like a graphics card is basically a mini computer in your computer, and the GPU would be the processor of that. So so you see, the GPU is pretty easy to find, and around the GPU you will always find these little things here, and then these 2 are empty pads for them, and here we've got them, and on all the other cards you'll already see them. That is the video RAM, the video memory. So like the 1060 got 6 gigabytes, the 980 has 4, the RTX 2080 has 8, the 980 Ti has 6, the 470 has 1.2 gigabytes, and the 560 Ti 448 also. So all of these cards are GDDR based. So except for the RTX 2080, they all have GDDR5 graphics memory, whereas the 2080 has GDDR6. But it looks pretty much the same. There is another version of video memory, which I do not have here on a picture. That is HBM, and HBM is, well, it's also video memory, but it will not be in the form of a black chip on the PCB like this. It will be integrated into the GPU, so you will have like little dies right next to the GPU die, or in case of a RX Vega from AMD, you have 2 larger ones down there, and that's pretty much HBM. But HBM is pretty rare. You mostly see it on data center focused, server focused GPUs from NVIDIA, and the Vega graphics cards from AMD, and also the Fury graphics cards from AMD. Other than that, you will pretty much always see GDDR video memory. So these are always the little black squares around the GPU, and sometimes you also have something like this. That is an empty soldering pad. So Gigabyte probably uses the same PCB for a GTX 1070, which would have 8 gigabytes. So they slap 2 more on there to make 8 out of the 6 gigabytes on this card. So that's pretty much the basic stuff, because every graphics card has a GPU and memory, so you'll always find it will always look like this. Like, you have that deviation with HBM memory, but since it's rather rare, that is the most constant thing you will find on every graphics card. Then there are some less constant things, but that these things will also always be there, which is first the power connectors and your video out, and the PCI Express slot, of course. So all of these cards have those three things. Certain graphics cards that are really, really low power do not have power connectors, but if you have one of these cards, why do you analyze the PCB of it? Because obviously it's not really meant for overclocking. So yeah, you can see it. There we have the power connectors of all the cards. You can see there are two different versions also. There are 8 pins and 6 pins. Here you can see this one right here is an 8 pin. It has 8 connection points, and this right here is actually a 6 pin. The plastic part is the size of an 8 pin, but it's actually a 6 pin, so you see those two contacts are missing here. And then like these are just normal 6 pins. And basically a more power hungry card will have an 8 pin, like this right here, the 980 Ti has 2 8 pins. And yeah, so there's not that big of a difference between a 6 and an 8 pin. The 8 pin basically has one extra ground connection, and the other extra you add is a sense pin, so the card knows whether the 2 extra are plugged in or not. So yeah, and then like you always have a PCI Express slot and your video out. That is always there, because otherwise it wouldn't be a graphics card. And then you also have stuff like this, which are SLI connectors. Now you don't see these anymore really, because these are the old kind of SLI connectors. This is an old standard that's no longer used in modern GPUs. If you have a graphics card from NVIDIA that supports SLI, you will see this. That is an NVLink connector, and that's basically just the new standard that SLI uses. But since SLI is becoming less and less really usable, and it's being slowly phased out, you have more and more cards which just don't have these connectors. And on AMD, those connectors, they had something similar looking back in the day, but for several generations AMD doesn't have extra connectors for multi-GPU. So if you have an AMD card, you just won't have that, except it's super old, like it's an HD 7970 or something like that. So, and now we get to the juicy stuff, the stuff that's actually that's the stuff that people have questions about, the stuff that is interesting. Because so far we've just gone over what you will find on every graphics card. Now we can get into the stuff that can make a good graphics card or a pretty bad one, and that is the VRMs. So you will see that apart from the little black squares, which are the VRAM, you will also see some more, even smaller black squares on all those GPUs. Those are the Mosfets, and then right next to them there are these very often they are gray boxes, which are the inductors. So on our 1060 over here we have an inductor here, and then all those other are also inductors, and then we have Mosfets here. Those make up VRMs, and you can see that these are quite different from card to card. You have smaller ones, you have pretty big ones, and you can have some that have something missing in between. So VRMs are pretty different. Basically, the VRM will be the biggest difference between a, say, GTX 1080 from one brand to a GTX 1080 from another brand. And yeah, there are different kinds and how you can implement VRMs. So the most common VRM will just look like this. So you have one big block over here, which is your vCore. Then you have a smaller VRM, which is vMem, and then you will have find like one inductor down there, which is vPEX. vPEX is not really, it's not really important. Like there's another PEX rail. Not really that important. What important is vCore and vMem, and also VDDCI. AMD cards have another VRM, which is VDDCI. I don't have any AMD cards on here, sadly, and actually I only have one AMD card, and yeah, as to compare to my whole load of NVIDIA cards. So when it comes to VDDCI, I do not have enough experience, let's say, to really get into VDDCI VRMs, so I'm just gonna say it's there. Most of the time it can be a little larger than a vMem VRM or the same size. So let's get back to the basics again. So here we have vMem, and then we have vCore. So the V stands for voltage, because the VRM supplies your voltage and your power that you need to drive your graphics chips and all the other things that make calculations on your graphics card. So vCore, pretty obvious from the name, goes to the core of the card, the GPU, and vMem goes to the little memory chips on the card. And since the core sucks a lot more power and is a lot like, if you the core needs better voltage regulation, so it's yeah, okay, basically the core needs good voltage regulation, whereas memory chips can be okay with a little less quality voltage regulation, which is why the vMem VRM is so small compared to vCore most of the time. So then here on the 1060, here we have vMem again, so that powers our 6 GB here, and then here we have vCore, and that's actually a special layout, you see, because you see on here vCore is on the left side. It can be on the left side, but you see on all the other pictures it is on the right side, because most of the time the core is slightly to the left, mostly above the PCI Express connector. So you have the most space on the right side, which is where you would put a VRM. But there are cards which use a special layout, like this GTX 1060 here. You will see it on more budget cards, or cards that don't draw that much power, or cards that just don't need that big of a VRM. This one is actually pretty big already, but you can see how far offset from the PCI Express slot this core is, so they have enough space to put the VRM on the left side. This layout is actually pretty common for AMD's RX 400 and 500 series cards. If you have one of these cards, you will pretty much always have your vCore VRM on the left side, and then vMem and VDDCI on the right, like here. And yeah, there are also certain NVIDIA cards like this GTX 1060, a lot of 1050s and 1050 Ti's do this. The Reference GTX 970 does this, if I remember correctly. There's nothing really bad with having the vCore VRM on the left side, it's just a uncommon thing. So there are slight differences for having it on the left side, because your power, basically it has to travel all the way from the connector over there and then back into the core, which is on paper slightly worse than going the power through there and then into the core. But like it's not really a measurable difference. So yeah, vCore can be on this side, but you can see here again vMem here, vCore over here. And then on this RTX 2080, you have one big strip of VRM. You can actually see which is vMem and which is vCore from the inductors, because you can they have different inductance values. So this one right here has 22 and this one has 47 as its inductance value, which tells you that it is used for different VRM. So yeah, that's how you can find out. Then over here we have again a really big vCore VRM, and then vMem is over here. Like if you can if you can put vCore on the left, you can also put all the other VRMs on the left. Then over here again there is our little vMem, and then here's our big vCore VRM, which is again special because you can see here it is 90 degrees rotated to the right or to left. I don't remember how that works. So yeah, that's basically how VRMs can be laid out and how you can identify VRMs. Like VRMs look like this basically. You will always have a strip of inductors and Mosfets right next to it. Oops, I deleted the 980 there. So, and then there are basically these two variants. You can either have a VRM with Mosfets, so with discrete Mosfets. So you have in one phase, I'm gonna get to VRM phases a little later. So you have 3 Mosfets, for example, in a phase, or you have one power stage. The power stage integrates at least 2 Mosfets, which is a high side or low side. That I'm also going to talk about later. So, and now, yeah, let's get into VRM phases. So the most basic version of counting your VRM phases is just counting the inductors. So here we would have 1, 2, 3, 4, 5, 6 phases, and then 1 phase for vMem, obviously. And most of the time you will be accurate with this, but you can also be wrong with this, especially on motherboards. Counting the inductors will most of the time not give you the actual count of your VRM phases. A good example of this is here. You have 1, 2, 3, 4 inductors, but if you count the Mosfets, because I've already told you that you have 3 Mosfets in one phase, you end up with more than 4 phases. Because this VRM I actually don't completely know, but there's basically just this one way in how it would make sense, because this VRM is actually a 6-phase. It's just using 4 inductors. So those on the outer inductors, those 2 phases which are so tightly together, those share the inductor over on the left side. So that's one way how you can have actually more VRM phases than you can count, but most of the time you will see something like this, where you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 inductors, but it's not 12 phases. You have all your power stages over here, or you would have all your Mosfets over there. So again, these power stages integrate Mosfets, but it's actually not a 12-phase, it is a 6-phase, because this VRM is doubled by these little things right here. These are doublers, and how they work, to understand how they work, you have to understand Pwm controllers. The Pwm controller is this right here, and these Pwm controllers, they are not just good to find out how much phases you have. They are also a really important part of the VRM actually, and they can tell you how good your VRM is. So this Pwm controller, it controls the VRM phases, and for each phase it can control, it will send out 1 Pwm signal. And if you can find out which Pwm controller you are using, you can find data sheets in the internet by putting in the number that's written on it. For example, so this over here is a Pwm controller looking chip. Pwm controllers are mostly this size. It's not always a guarantee that they are Pwm controllers, but if you see a chip this size in this region of the PCB, you can be pretty safe that it's a PWM controller, and if it's not, you will find out when you put in the numbers that are written on it. So you can see it on the photo, but there will be written something like UP, and that font is way too big to... Oh. There will be something written like UP1912, and that's a UP9512. Yeah, UP9512. That's the pretty much standard PWM controller for NVIDIA's 20 series. For the 10 series it was the UP9511, and then so this card has its PWM controller right over here. I actually don't know for the 900 series, but on the 700 series, which we use very similar PCBs, it was the NCP4208. And yeah, so basically by looking at that little chip, you actually can't see it on this card because it is very likely on the back. Here we have another PWM controller. This card also has it on the back. It's about here on the back, and then yeah, I already showed you the PWM controller on there. So if you put it in into the internet and you search for it, like you search for NCP4208, you will find a datasheet for it. You don't always find datasheets for the PWM controller, sadly. Like if you have an ASUS card, the PWM controllers will be rebranded, like they will be SHE or DigiPlus something, and you will not find datasheets for these because these actually don't really exist. This is just a name from ASUS that's given to the PWM controller, which is actually a different part, something like some UPI semiconductor or international rectifier PWM controller. So if you have an ASUS card, you will very likely not find a datasheet for the PWM controller, sadly. But on other cards, if you put it in, you will very likely find a datasheet for it. So you can always be unlucky and have that one PWM controller that does not have a public datasheet, but very, very likely you will find a datasheet in the internet. And in that datasheet, it will tell you how many PWM signals that PWM controller can put out or does support. So in case of the NCP4208, it would be 8 PWM signals. Or for the UP9512, it would also be 8 PWM signals. And then for this controller right here, sadly you can't find the datasheet, but these doublers also have a name. They have a part number on them, and then if you put these in, you will find out that they are doublers. And you will find in the datasheet, so I found the datasheet, and it was written there that they take 2 PWM signals and they turn it into 4. So these are basically 2 doublers in one chip. And what that means is that the PWM controller can only be a 6-phase, can only be a 6 PWM signal controller, because what it does is it sends 2 signals to each doubler, and then the doubler will make 4 out of these. And that's how you get to all those 12 supposed phases that you have. So this is actually a doubled 6-phase on this card. This is better than just having a 6-phase, but for the PWM controller you only have 6 phases, and it's up to the doublers to determine how the VRM is handled. So some doublers, maybe they just send every other phase, they just send the information for every other phase to the PWM controller, or they split the information up between. And yes, so if you have doublers, the PWM controller, it lacks information basically. It doesn't really know what's happening. It will be slower to respond to changes in voltage and such things. But it is still a lot better than just a 6-phase. because it does improve your current capability and your efficiency and also your voltage regulation quality. And so having doublers is not bad. It's just that it would be inaccurate to say you have a, in this case, 12 phase, because it is actually a double 6. So what I would say, it is a 6x2 phase and not a 12. And then yeah, so another example of VCOVRM would be this. Here you have 1, 2, 3, 4 inductors, and it is actually also a 4-phase. This card uses discrete Mosfets. And yeah, the Pwm controller on the back, I think it is an NCP 5388 if I remember correctly. But I did find the datasheet for the Pwm controller on this card, and it was a 4-phase. So this is an actual 4-phase, and now I can also get into Mosfets. So power stages, you just have to find the power stage. But Mosfets are a little bit easier to find information for, because you know what your low side and your high side will be. And yeah, I can't fully explain what a low side and a high side MOSFET is right now. That would really blow up the length and the complexity of the video. I would just tell you to watch the video from Bullseye, or actually Hardcore Overclocking, on this. He does a pretty good job of explaining how it works. I'm just gonna stick to the explanation that the high side MOSFET turns your 12 volts that comes from the power connector into the voltage that your GPU core wants, and the low side MOSFET, it handles the current and does some other things. So basically what you have to know is the low side MOSFET is the more important one, because it handles a lot more current. And so yeah, if you look up a datasheet for MOSFET, what you want for your high side MOSFET, you want it to be fast, and your low side MOSFET, you want it to handle a lot of power and have the lowest possible RDS on resistance. So the RDS1 resistance is the resistance of the MOSFET that the MOSFET has when it's turned on. And the higher your RDS on is, the more heat the MOSFET will put out, and the more power will get wasted in the VRM. And that's obviously bad, because you don't want your MOSFETs to get too hot, because when MOSFETs get too hot, they blow up. And when MOSFETs blow up, especially the high sides, you will introduce short circuits, and you will basically have a dead graphics card pretty fast. And then for power stages, there's basically the same thing. It's just a little harder to find all the specifications, since it's basically a lot of things in one. Power stages also include drivers, which can also be doublers. So doublers, drivers can be the same thing. Like this card does not have doublers, but it has these little chips right here, which I can't find it for that phase actually. Did I cover it somewhere? Yeah, there's a 4th chip somewhere in the VRM. These are the drivers for that VRM. They're not really that interesting, except for when they are doublers. So yeah, and then let's just, I think I explained all the most important stuff, so let's just go over all these PCBs, and I'm gonna tell you what they are, so you can watch the process basically of how I would do something to determine what a VRM is. And that should give you a pretty good idea on how to handle your graphics card PCB. So first we have the GTX 1060 from Gigabyte, and the first thing I look for is always the VCOVRM. So here we have 1, 2, 3, 4, 5, 6 inductors. We do not see any doublers. They could be on the back, but GTX 1060s, they draw about 120 watts, I would say. Having a doubled 3-phase, like doubling 3 phases doesn't really make sense to me. So the lowest phase count you would double is generally a 4 phase. It does happen that 3 phases get doubled, but I don't think I have seen it on graphics cards yet. I think I have only seen it on certain motherboards. So the fact that we don't see any doublers, sadly we can't see the Pwm controller, which would give us a definitive answer of how many phases these actually are. Because what is also possible is that this card could have a Pwm controller with only 3 phases, and the Pwm signal, so imagine the Pwm controller would be here, and it gives out 3 Pwm signals. What could also be possible is the Pwm signal just goes into 2 phases. That is also possible, and that would be what I call a big 6 phase. That is possible. You see it a lot on motherboards, and you can also see it on high-end graphics cards actually. My RTX 2080 Ti, which is a Gigabyte Aeros Extreme card, it has 16 phases worth of components on there, but the Pwm controller on it, which is the UP9512, can actually only support 8 phases, and there are no doublers on that card. So these 16 phases are actually 8, and there's just one Pwm signal going into 2 physical phases. So it's actually an 8 phase. So I'm like, physically there are 16 phases, but functionally it is 8 phases, and I always talk about how it is functionally for the card. If I say it has that much phases. So, but back to this card, we can't see any doublers, and it wouldn't really make sense to run a 3 phase on a GTX 1060, so I'm gonna say this is a 6 phase. If you have this card in your hand, definitely look up the Pwm controller and find out if I'm right. And yeah, then we see our Mosfets. This card is using discrete Mosfets, and what you're gonna see a lot of the time is that you have 2 low side Mosfets, because, well, your low side has to handle a lot of current. And those 2 low side Mosfets will be put in parallel, and if you put them in parallel, each of them only has to handle half the current because it is split between the 2. So you have 1 high side MOSFET per phase, and then you have 2 low side MOSFETs per phase. Sadly, I also don't know which exactly these are. You could now look up the part number that's written on them and see what values they have, what RDS(on) they have, how much current they can handle, basically how good the MOSFET is. And yeah, so some cards also have 2 high sides in parallel, like the GTX 580 Direct CO2. It has 2 high sides, but that's pretty uncommon. If you have discrete MOSFETs, your VRM will basically look like this. So VCore VRM is very, very likely a 6 phase, and I would have to look up the specific datasheets for the MOSFETs to tell you how good this VRM is. You can apply the same to the VMem VRM. Most of the time that's just less exciting. So you have one inductor and also one, like it's just going to be 1 phase. Because you only have, like, that's your high side MOSFETs and these are the 2 low sides. And so you've got your 1 phase of VMem there. Like, when overclocking VCore is always going to be the most interesting VRM, because yes, you can overclock memory, but you can not really give it more voltage. On some AMD cards you can give it more voltage, but even then the VMem VRM is pretty not really that interesting, because most of the time VMem is using way too powerful MOSFETs for what it actually needs. So you will basically never max out that VRM or not even get close to it. Whereas on VCore, cheaper cards can max out their VRMs a lot, like the this card over here has a very, very low voltage limit compared to this card. Those 2 cards have a very similar GPU. It has the same amount of cores, it just has a different name. They also have the exact same amount of video memory. But the upper card can go on higher voltage because it has a 6 phase instead of a 4. And it is also cooled better. So if you cool your MOSFETs better, they will handle more current basically, and yes, keeping them cool will not make them blow up. So then over here our GTX 980. We already see from the size of the GPU and from the amount of power connectors and also from the amount of memory chips we have here that this is a more powerful card. And the VRM reflects that. So let's get VMem out of the way. It's a one phase again with discrete Mosfets, pretty unexciting. And then vCore over here, which is again the special version that is actually 6 phases, but with four inductors. So I would prefer having one inductor each for each phase, but it's not really that much of a problem. It's just the inductor will have to handle more current. So if you push too much current through the inductor, it will burn out sooner than having one inductor for each phase. But inductors are not really the first thing to burn out. It's mostly your high side or your low side MOSFET which will blow up. Like high sides will blow up if they get too hot, low sides will blow up if you push too much current through them. Both also go for everything, but since low sides have to handle more current, these are more likely to blow up because of current. So again, then we have also your Pwm controller, which I think is an NCP 4208 or a newer version of it, which is an 8-phase actually. So you see that there is enough space for 2 more phases. So this could theoretically just be a PCB that can handle 8 phases, but they just cheaped out a bit and didn't put these on. So that can happen if it's a PCB that's also used for another card that has that needs more power and needs a more powerful VRM. Or this could also be just not an NCP 4208, and it could also be a 6 PWM signal PWM controller that can only handle these 6 phases. And yeah, so you will basically see empty soldering pads when the PCB is used for several graphics cards with varying amounts of power requirements. And yeah, you will see it on cheaper cards, and up to the GTX 980 Ti, Nvidia's reference PCBs were pretty cheap. This is post 1080 Ti, so this is a very much better PCB than the previous Nvidia reference PCBs. So here we see for the first time that power stages are used. And power stages compared to discrete MOSFETs are very efficient, and they can handle a lot of current. But the thing is, yeah, like they integrate several things. So yeah, they are a bit more complicated, and when it blows up, it will most likely take the rest of the power stage with it. Like you can't use it anymore if one of the things in power stage blow up. But with that said, you can be lucky if the card even works after that. So here we would see our vCore Pwm controller. What I forgot to mention is VMem obviously also has a Pwm controller. It can happen that it is just also using the, yeah, that could also be the case on this card, that it's just the NCP 4208 which also controls VMem. But most of the time you will have a second Pwm controller, a really small Pwm controller somewhere on the card. Like this could be it from what I've seen. This could be the Pwm controller for VMem. So yeah, every VM needs a Pwm controller, obviously. So yeah, back to this one. We see 1, 2, 3, 4, 5, 6, 7, 8 vCore phases and 1, 2 VMem phases. The Pwm controller is a UP9512, which is an 8-phase controller. VMem VRMs generally don't get doubled or use the big setup. For VMem, it's just 99.9% of the time it's the amount of phases which you count as inductors. So this is a 2-phase. I know for a fact that this is a 2-phase, but like you don't really have to look up the Pwm controller to find out. So again, here we have our card with the doubler VRM. So here we would count 12 inductors, but it's actually a 6-phase because we have these chips right here which are doublers. And if this wouldn't be an ASUS card, we could also look up the Pwm controller, how many Pwm signals it supports, and then find out it's only a 6-phase Pwm controller. Then over here we have VMem. These are 2 phases, and that's also the Pwm controller for Vmem. This one you can actually look up, because that is, ASUS generally doesn't rebrand Vmem Pwm controllers, only vCore. So you can also find out that this is a 2-phase. And what's also interesting here is vCore is using power stages, whereas Vmem is using discrete Mosfets. Most of the time you will see that both VRMs use the same Mosfets or power stages, but it can also be something different, like on this card. So then we have our GTX 470 reference PCB with our 90 degrees rotated VRM. This is a 4-phase, as I've already said, and then a 1-phase Vmem. Yeah, again, the Pwm controller here is on the back. If you look it up, you will see it's a 4-phase, and then somewhere here on the back there's also another Pwm controller for Vmem. So we'll find that out. Then here we count 1, 2, 3, 4, 5, 6 phases. And here is the Pwm controller. If we look this up, we will see that this is also a 6-phase, 6 Pwm signal controller, so this is a real 6-phase. On the back we can see chips that look similar to this, but in this case they are just drivers, not doublers. They only drive, they don't double. And then we have our 1-phase Vmem over here, which also has somewhere on the back there's gonna be a Pwm controller for it. So yeah, that's pretty much how you find out your VRM phases. And now I gotta talk a little bit more about the Pwm controllers. So if you look up the datasheet for the Pwm controller, you will not only find how many Pwm signals it can deliver, but you will also find a switching frequency listed. And the switching frequency is basically, it's this: having a higher switching frequency will make the voltage regulation of the VRM better. It will put out a more consistent voltage. Like if you look up the video from actually Hardcore Overclocking Bullseye that I recommended, if you watch this, you will know that VRMs do not put out a static voltage, they put out a fluctuating voltage, and having a higher switching frequency will make that fluctuation less. But having a higher switching frequency will also make efficiency worse. It will make the MOSFETs turn on more per second, therefore they are more active, therefore there is more power going through them. They're not really, like, they are being used more, they are active longer in a specific period of time, which means there is there is more power wasted in the MOSFETs, and there is more heat generated in the VRM. So it will make the VRM run hotter, and it will make your efficiency of the VRM worse. But it will improve the voltage regulation, which could theoretically help you in overclocking, because having less fluctuation will mean you have you have a steadier voltage because of that. And having more VRM phases obviously helps with that, but you'll also have to watch Bullseye's video for that. And yeah, so high switching frequency is good, but having one too high is also bad again. So for example, the UP9512 of our 2080 down here, it can go from, I think, 1 megahertz, or is it 0.5 megahertz? I don't know, but it can go up all the way to 2 megahertz, which is very, very high. And I don't think any card will use this. Most cards will probably be somewhere between 500 to 700 kilohertz. And then Vmem VRMs will be somewhere around 300 kilohertz. And yeah, so some Pwm controllers have variable switching frequency, which you can actually change if you have a soldering iron and the datasheet and enough expertise to do it. But there are also Pwm controllers like the Vmem Pwm controller of the GTX 470, which just has static 300 kilohertz. So yeah, but that's basically it. This video is already 45 minutes long, so yeah, And I also think I have said enough now. So yeah, this is what you will find on a graphics card. This is how you identify your VRM, how many phases you have, a slight look into how good it might be. And yeah, so again, the basics: more PWM phases, more better. Doubled is better than just having a big phase. So having a doubled configuration is better than a big configuration, and a big configuration is slightly better than a normal configuration. And yeah, so more phases, more better. And yeah, more switching frequency, also better for voltage regulation, but it will also put out more heat. It will make your efficiency worse. And then for Mosfets, obviously, like for the low sides, more current capability is of course better, and lower RDS(on) resistance is better. That also goes for the high sides, but the high sides do not have to handle as much current. So high sides will pretty much always have higher RDS(on) and less current capability, because like they are high sides. You don't need as much on there. So, but yeah, that should be it for GPU PCB basics. And as a little bit fun to the end, we could also go over the PCB that I've drawn. So here we have our Pwm controller for vCore. vCore is over here. That is a 6-phase. Pwm controllers over here. Then we have our 2-phase. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 memory modules, which is a number you will never see in real life. It will be pretty much like, not all memory modules have the same amount of capacity. So you will have like 3 GB cards which have 12 modules. You will have 4 GB cards which have 4 modules. You have 6 GB cards with 12 modules. So yeah, it's basically just high-end cards will have more modules than low-end cards. Like you see here, that one has 6. This one here, it has 8, so 8 again. This one on the 2080 also has 8. This one has 12. This one has, yeah, these two have a weird number. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yeah, and like the GTX 1060 has 6 GB, the 980 has 4, the 2080 has 8, the 980 Ti has 6, and the 570 and the 560 Ti 448 have 1.2 GB. So yeah, that's not really important. Then we have our imaginary CMD 780A1 GPU over here in the middle. PCI Express slot, our power connectors, and then our video out. So yeah, that's GPU PCB basics, and I think this video is long enough already. So I'll be seeing you again next time. Goodbye.